The broadcast is now starting. All attendees are in listen-only mode.
Hey, welcome everybody. Coffee with Caleffi. Thanks for joining us today. And that's also thanks for your support of Caleffi. We appreciate each and every one of you, and input's always welcome. You know, we love hearing from you. Whatever we can do to help you out or make our presentations better, let us know. So thanks. Proud to introduce my friends and colleagues. Kevin and Cody are going to be doing the presentation today. They did a great job putting this together. I think you're really going to enjoy this one. I know Kevin and Cody both put a lot of time into this, and it's a timely topic. So we're going to let them show you what they've been doing all week. Hydronics, number 20, you should have right now. Hopefully everybody that's listening in today is getting these. If you don't, there's the web address at the bottom that you can go and sign up. These are free. Twice a year we send these out. By far one of the best technical journals in the industry, I'm proud to say. I think if you've been receiving those, you will agree with that. But those are some of our back issues there, and let us know if you do want some of the back issues. We can help you with that also. In the hard copy, they're online. What do you got next, Kevin? I think you're ready to turn it over to you.
Okay, thanks, Bob. Yeah, today's topics, we'll cover a lot of things. We'll talk about what is a high-low. We'll talk about the definition of flow ranges, when to use this kind of a valve. Does Caleffi have a solution? And how do they work? We'll cover in detail how these types of valves work and how to commission them. Cody will cover that part, and we'll touch on recirculation too. We get a lot of questions about recirculation. So, all right, let's go ahead and jump into it. All right, the definition of a high-low, it's really an industry term, kind of a loosely used industry term that describes a type of valve or a valve assembly that can handle a broad range of flow. So a broad range of domestic hot water flow is typically needed in institutional places and commercial applications like hotels, hospitals, schools, large residential homes. For example, when we talk about a wide range, the valve might need to deliver tempered water at 1 or 2 GPM of demand, or even up to 40 to 50 GPM when multiple fixtures or high flow fixtures are flowing or consuming water simultaneously. So pictured here are some established and popular high-low thermostatic mixing valves on the market today. We've got on the left here a model from Simmons. We show a picture of Lawler, Bradley, Leonard, and then the new Caleffi Delta 2. So we will cover that in detail. What we won't be covering are digital mixing valves today. That's going to be a different webinar. Here's a cool picture. This came in on the Caleffi Excellence Contest, and it shows a high-low valve in that red circle. And you can see here also there's a recirculation pump. Down below, a couple of bouncing valves. Those are Caleffi low lead quick setter plus bouncing valves. It's just a real nice shot we wanted to share with you. So let's talk about the different types. Some of these high-low valves are what I call a unitary body. They have a thermal element inside that can cover a broad range of flow, or they have a wide rangeability. So that's one type of high-low valve that you'll see out there. And you can see here the two inlets. The red is the hot water inlet, the cold inlet, and then the mixed tempered outlet here. The other style of a high-low is an assembly, and here's a picture of one from Honeywell. What this has is a small mixing valve shown right here on the right side, and a large mixing valve, and they're piped in parallel. So the hot water comes in, it flows into both valves at the same time, and the cold water does the same. The cold water comes in and flows into the valves as well. Downstream of the large mixing valve is a PRV, a pressure reducing valve, and we'll get into detail on how that works. But this is a common assembly, and I'll show you some more pictures of what those look like. You can build these yourself, actually, and we have received a few pictures of that. This picture on the left shows a couple of high-low assemblies. This actual project is a prison, and the picture on the right is basically the same thing. This is a hotel, a large hotel, and you can see on the right, this Caleffi mixing valve right here is a big 2-inch mixing valve. So they have a small 521 series and then a nice big 5231 series pipe together. Here's another shot that Mark took. It's another field fabricated high-low assembly. You can see a large mixing valve on the left, a small one on the right, and then a PRV up here downstream. So those are some pictures that show you how these built-up assemblies look. So right now, let's get into looking at how an individual valve works. To really understand how the assembly works, we need to look at the details behind a single valve. So here's a cutaway of a Caleffi 521, the smaller body mixing valve. And how that works is, as water is drawn out of the mix port, hot water and cold water come into these two inlet ports, and those two streams of flow mix in this area around the thermostat. And when the water temperature around this thermostat is higher than the set point that you dial in on the knob, that thermostat will expand and close off this hot port, at the same time opening up the cold port, and vice versa. If that thermostat cools off compared to the setting on the knob, it will retract and close down the cold port to open up the hot port. So that's the basic functionality of how that works. Now, what we want to talk about is the minimum. These valves all will have a minimum flow rating, and the rating is based on the thermostat stability at low flows. What's needed here is the thermostat has to have some well-mixed water to provide stable control. So we have to have enough velocity coming in both the hot and the cold ports so that that water mixes and is nice and turbulent around the thermostat, so it can provide good steady control. If the flow is too low in a thermostatic mixing valve, what can happen is the flow will be fairly laminar, and when it comes in, it won't mix well around the thermostat. So you can get some hot and cold pulses around the thermostat and cause that thermostat to hunt. And what that does is it means that the mixed water temperature is going to be inconsistent, and you'd be able to feel that out at the fixture. The water might be getting, a little bit hotter, a little bit colder coming out of that mixed valve. So it's important to have enough flow in a valve like this. Most residential projects that use, say, half or 3/4 or 1-inch valves will have a minimum flow rating that is enough, to deliver to a single fixture. Like this valve we're looking at here can control water down to, the consumption of a single fixture, like 1 GPM. Some of the valves like this are a little lower, some of them are a little bit higher. So I hope that's helpful in determining or understanding what the minimum flow rating is all about. A maximum flow rating on a thermostatic mixing valve is more difficult. A lot of manufacturers don't even specify what that is. Ideally, what you'd want to do is rate a maximum flow at the GPM value that the valve can function and perform within spec, but not make noise or be damaged by the water velocity. And depending on the piping characteristics, this can really vary. So you can see my notes there that it's really based on a reasonable pressure drop and a reasonable velocity. And a lot of manufacturers will give you a differential pressure versus flow curve that you can look at. And of course, if we have too much flow, too much pressure drop, that will result in noise and erosion. So let's talk about that a little bit. I want to refer to a guideline from the Copper Development Association here of a maximum recommended velocity in hot water piping. Now, if your water is up to 140 degrees Fahrenheit, 5 feet per second is the maximum recommended velocity. And by the way, this is also in the Uniform Plumbing Code. So that is, why would we do that? Why would we have a maximum? If you go above that, you're looking at erosion, corrosion, noise, vibration, and even some pitting in the piping. And if you look at different size pipes, 5 feet per second in a 1/2 inch copper is 4 GPM approximately, and 3/4 is 8, and then 14 GPM in a 1 inch copper pipe. So, okay, this is a guideline. How does this relate to the maximum flow rating of a mixing valve? Let's take a look at some common thermostatic mixing valves that are used in 1/2 inch and 3/4 and 1 inch lines. And what I have here is a flow characteristic curve for a valve that has a CV of 2, just for example. Okay. Now this line right here, this curve, represents the formula differential pressure equals flow divided by CV squared. So that's what this curve represents. Let's look at an example. Say you had a valve of with a CV of 2 and you were flowing 4 GPM through it. 4 divided by 2 is 2. So if you square that, the pressure drop is 4. So if we look up here and come across, that's about 4 PSI differential across that valve. Another value, 8. So 8 divided by 2 would be 4. If you square that, we're looking at a pressure drop of 16. Let's look up here at the high end, 14. If we were able to pull 14 GPM through a valve with a CV of 2, what would that look like? Okay, 14 divided by 2 is 7. If you square that, that's 49. That's right up at the top of this curve. Now, think about that for a minute. 49 PSI pressure drop across the mixing valve. That doesn't leave a lot for the rest of the piping and the fixtures. So that's too much. So what's my maximum flow for this valve? All right, well, Caleffi recommends to stay at least most of the time beneath 20 PSI differential, less than 20 PSID across a mixing valve. If you increase that periodically, that may not be an issue, but that's a guideline that we use, and we show that in our literature. So this means what for this particular valve? A differential pressure of 20 equates to about 9 GPM. So a valve with a CV of 2, we would say, try and stay below 9 GPM. Now, some vendor literature will show tables and charts that have really high differential pressures, and the valve might work under those conditions, but you may have issues. So just keep that in mind. So looking at the velocity guideline above and this valve with the CV of 2, could we put this valve in a 1/2 inch pipe that was designed to deliver 4 GPM? Sure. Here's 4 GPM. We're down here on this point in the curve. We're below the 20 PSI differential. Could we put this valve in a 3/4 inch pipe and flow 8 GPM through it? Sure. We're still below that 20 PSID. We're at about 16, as we mentioned earlier. Okay. You wouldn't want to go up to 10 feet per second in a 3/4 inch pipe, because you'd be above the differential pressure. So I hope that makes sense. If anybody has any questions about this, type those in and we'll answer you.
Hey, Kevin, if I could add one thing to that too, is this becomes really critical if you're going to use a thermostatic mixing valve on a pump system for maybe mixing down a radiant temperature or something like that. Think about that pressure drop, and the pump that you're putting in that circuit now has to overcome the pressure drop of that valve. So when people buy a 2 or 3 CV valve and tell us they want to start putting 15, 18 gallons a minute through it, that's where you look at this chart and say, well, probably not going to happen with a little circulator pump. So it plays in on a pretty big pressure drop when you start pumping through these valves also.
Yeah. So I hope this information is helpful. What if we had a CV of 3? And by the way, this Caleffi valve right here has a CV of 3. Okay, you get more capacity, obviously. So where would the maximum be at 20 PSI differential? So this valve will easily pass, that's approximately just under 14 GPM. So we went from 9 GPM to 14 GPM at the same pressure drop just by going from a CV of 2 up to a CV of 3. So small valves work well at low flows. That's pretty much sums up what we just talked about. And there again, that's the Caleffi 521 down below that has a flow range of 1, and we're going to call the high end 14 GPM at 20 PSI drop. Okay, large valves, they're out there. You can buy those. There's a Caleffi model on the bottom that has a CV of 14.2. Notice that has a minimum of 8.8 and a maximum of 70. Okay, now we know that a lot of large valves are installed, to give more capacity, but the low end is the problem. Remember, we talked about like laminar flow. If you put that big valve in a pipe and try to flow 1 or 2 GPM through it, that thermostat is going to probably hunt, and it won't know where to settle in, and you probably get inconsistent water temperature. So you can't just put in a big valve to handle that, because you lose the low end. So what do you do if you have an application like this? You need to deliver tempered water for one fixture, but you also need to be able to deliver enough water for multiple simultaneous showers. It's a nice shower. Well, the plumbing designers, or whoever is figuring out how to design the plumbing and size the plumbing system, they'll use tables like this called fixture units. There are other references. Some manufacturer literature has some other information, but basically someone who's designing the system has to determine what that maximum is. And you don't just add up the GPM of all the fixtures. This fixture unit isn't a flow rate, but it's a design factor that's used in designing plumbing systems. So we're not going to really get into this because that's not part of this webinar. I just wanted to show you how the maximum is determined in larger systems. All right, switch gears just a little bit. Yes, Caleffi does have a solution. This is called our Delta 2 series high-low valve, the NA523. There's a picture of it. I'll go through some of the features. It's one model right now with 1-inch sweat inlets and 1.25-inch sweat outlets. The 521 you can see on the bottom, the red circle, that's our small 521 series mixing valve. Piped in parallel with a 5231, that's 1.25-inch mixing valve. And both of those have checks on the cold water inlet. Downstream of the large mixing valve is our PRV, our new 535H series high flow, high performance PRV. It's a highly engineered pressure reducing valve, top of the line. So this assembly will deliver from 1 to 50 GPM as you see it here. It has lockable settings on the PRV and the mixing valve, so you can minimize tinkering if you want to set those locks. And up on the outlet, there's a nice high quality screw-in temperature gauge, and you can take that out if you want to. If you wanted to put a pressure transmitter or anything like that in there, you could do that. It's a 1/2-inch NPT connection. And it comes just like it's shown here. It comes attached to strut and ready to hang on the wall. So that's a product that we're real excited to introduce. All right, at this time, we're going to throw a poll question out there. We want to hear from you what size high-low thermostatic mixing valves you use or specify most often. We would love it if you could pick one of those sizes, or if you don't use them, go ahead and select you don't use them. So we're going to launch a poll, and I'm going to just hold off now while that goes.
Yeah, and then one thing I would caution people when they look at different size valves, that sometimes just going up a pipe size from a 3/4 to 1-inch connection size on the valve doesn't necessarily give you a higher CV valve. So what you really need to be looking at when you start sizing these valves is the CV listing on that valve from the manufacturer. I see that mistake a lot of times where people say, oh, I'll buy a 1-inch valve and I'll have a lot more flow through it. Well, you got to look at the number to get the right answer to that question. And we see that again on radiant systems where they say, oh, I'll just put a 1-inch instead of a 1/2-inch valve, and it's the exact same valve, and then the CVs are probably going to be exactly the same. So it's not the pipe size that you're sizing your valves by; it's by the flow rate that you need to move through that valve to get them to perform properly. All right, so there's our poll. Wow, that's surprising that I don't use high-low mixing valves at 45%. So yeah, well, thanks for the information. That's a good use.
All right, thanks, Bob. So let's talk about these high-low assemblies. How do they actually work? We have a nice cutaway here, and let's look at how they actually work and how the flow passes through the assembly. So in the bottom are the cold and hot inlets. You can see the cold on the left and the hot on the right, and they come up. And of course, the valves are piped in parallel, so they enter the two inlets. The mixed water from the small valve goes around the big valve in the PRV right directly to the outlet. The mixed water from the large valve goes to the PRV and then to the outlet. And we'll get into great detail there. Now, the PRV, being a pressure reducing valve, is closed when the downstream pressure is above the setting on the PRV. So that's the fundamental function of a PRV, is it will open when the downstream pressure drops to a certain point, that being dialed in on the setting. So just in summary, under a low flow condition, the small valve is doing all the work, okay? And under a high flow condition, the PRV will open, and then both valves will be delivering flow simultaneously. And let's take a close look at that and see how that works. Okay, we're going to pick some numbers here just for conversation. Let's say we have 60 PSI on our supply line, and the PRV is set at 53. Now, ultimately, after Cody talks about the commissioning, the PRV might not be set at 53. These are numbers that we're just going to work with and use these as, just as a conversation. They are approximate, and we're not going to account for line losses in the pipe just to keep things easy, but I think you'll get the gist of the message here. All right, let's say we have a 2 GPM draw. What happens here? If we go back to the flow curve on that 521, we'd be looking at a delta P of about 0.5. So if we just put in, say, 59.5 across that small mixing valve, the rest of the system downstream is at 59.5. Okay. All the flow is through the small valve, and the PRV is closed. Why is the PRV closed? Because it's set at 53, and the downstream pressure is 59.5. Let's increase the flow, open up a few more fixtures. Now the delta P across that small mixing valve is about 2 PSID differential. So we've got 58 PSI downstream, and again, not counting for the piping losses here, let's keep it easy. Then we have 58 PSI downstream, delivering water to the system. Okay, now we open up a lot of fixtures. 8 GPM draw across that small mixing valve results in a differential pressure of 7. Now look at the pressure downstream. It's 53. So 53 is right at the same pressure as the setting on the PRV. So that's the point at which the PRV will start to open. I hope that makes sense. So any more flow than 8 GPM in this example, would mean that PRV would crack open and flow would start going through that larger mixing valve. So what that looks like graphically, on the left there, that small valve delivers, I said, 1 to 8 GPM approximately. The large valve by itself, if it were piped by itself, would deliver about 4.5 to 40. But when you combine them in this assembly, this is what happens. You have the ability to control from 1 GPM up to 50 GPM because the flows are are summed up between the small and the large valve. I hope that makes sense. So that's kind of a quick overview of how it works. I hope that's helpful. And what we're going to do now is bring Cody in, and he's going to talk to you about how this is all set up. Once you get it mounted, what's the process of commissioning it? So are you there, Cody?
Yeah, I am, Kevin. Thank you very much. And thanks to all of our listeners. I just, like Kevin said, I want to go over how this unit is commissioned, not only how, but why, because understanding what you're doing is half the battle sometimes. So the one thing that's great about our high-low assembly is commissioning it requires absolutely no special tools. It just requires a little bit of your time. And you might be thinking to yourself, well, the mixing valves are easy to set. You turn the knob, you adjust it to whatever your outlet temperature needs to be, and you're good to go. But where setup is incredibly important is with the setting of the PRV, and that's what we want to go over here, because if the PRV opens too early, then you're going to have issues with the mixed outlet temperature hunting again, because the large mixing valve is going to be flowing when there's only a little bit of flow going through the small mixing valve. But if it opens too late, then you're going to have increased pressure drop and high velocities through the small mixing valve. So let's just assume that, a standard system, you're going to want 120-degree tempered water out of the mixed outlet of the fixtures, or going out to the fixtures. So the first thing you're going to want to do, and this is going to sound weird, but you're going to want to set the small mixing valve to 110 degrees, and I'll get to the reason why here in a little bit. So you're going to want to isolate off the PRV with the ball valve. We do provide ball valves on each line to isolate the large one in the small mixing valve. And so you want to make sure to isolate that so that your only flow is going through the small mixing valve. From there, you are going to open up 1 or 2 fixtures to get into roughly 2 to 3 gallons per minute of flow. This is kind of the sweet spot for those small mixing valves, because as Kevin had mentioned previously, that our small mixing valve does have a minimum flow requirement of roughly 1 gallon per minute. And so to get it above that minimum flow, to get the velocity and the turbulence, to get a good mixture coming out of it. So once you've got that 2 to 3 gallons per minute, you're going to adjust the knob to where you're going to read 110 degrees at the nice gauge that we've provided for you on the high-low. And once you're done with that, you can settle in on that 110. The next step is going to be setting the large mixing valve to deliver 120. Now again, this is what you want out to your fixtures, is 120. So we're going to set that up. And the first thing you're going to do is very similar, isolate off the small mixing valve so that the only flow is going to go through the large mixing valve. Again, this is approximate, but you're going to want to flow roughly 12 to 14 GPM through that large mixing valve. Okay, and if you can just count up fixtures, I have this many labs, this many bathtubs, and just kind of go from there, or a tub sink or something like that. Just get yourself in the range. 12 to 14 GPM, again, the sweet spot for that larger mixing valve. And then once you get into that flow range, adjust that knob to where your mixed outlet temperature is reading 120 degrees. Now here is the interesting part as far as setting up the PRV. So while you're maintaining that 12 to 14 gallons per minute, you're going to open up the ball valve that isolates off the small mixing valve. And you're going to observe the outlet temperature coming out of the high-low. And if you remember back, we set the small mixing valve to 110 and we set the large mixing valve to 120. Okay, now if at that 12 to 14 GPM, if you are getting a mixture from both of them, you should theoretically be somewhere between 110 and 120. So what you want to do is adjust that PRV until you get roughly 112 to 114 coming out of the mixed outlet on the assembly. This is guaranteeing that your PRV is opening at the appropriate spot. Now, if it's closer to 110, that means you're not getting enough flow through the large thermostatic mixing valve to mix up the 110 from the small mixing valve. And again, if it's closer to 120, you're getting too much flow through the large thermostatic mixing valve. So that means it's actually going to be opening too early, and vice versa with 110, it's going to be opening too late. So once you've got the PRV set, you can lock that in place. Like Kevin had mentioned before, we do have the locking features to prevent tinkering. But then last but not least, you're going to go back to the small mixing valve, isolate off the large mixing valve, and set the small one back to 120 using that 2 to 3 gallons per minute as your sweet spot. Now, once you have set the small mixing valve back to your 120 degrees, what you want out to your fixtures, you can open up the valve, all the valves, and your setup is complete. It's really about as simple as that. I don't know if there's any questions. Feel free to shoot them out there if you've got them. We're more than happy to help you out. But again, very simple to do that kind of thing. So,
Cody, as long as you're here and you're asking for questions, sure. This might be a good spot if you can hear me. Yep. One thing I would say too is our pressure reducing valve, you can turn that with your fingers. You don't need to put a wrench on that. You can also put a gauge on the discharge side of that. It's available with or without a gauge. So if you want to say, well, how do I know what the pressure is in my system? There's no gauge on it somewhere. You can put the gauge on that PRV and you can make really fine adjustments with it. It's got a real fine thread adjustment on that knob that you just turn with your fingers to dial it in. But one question that I had, Cody, and this is a good one, what if the pressure varies on your system coming in, like you have a booster pump on your home or something like that, and the pressure can vary from, say, I don't know, 20 to 30 or kind of a wide range? How does that affect it? And the same thing could happen like if you had a water softener on your hot water supply in the building, you could actually have a different pressure on your hot water coming into a valve than you do on the cold. What do they need to be aware of when you have pressure that moves around like that or is different on the hot and cold?
That's a very good question, Bob. Now, all of our mixing valves have a ratio, pressure ratio that you have to fall within the range of, and it's actually pretty forgiving in the fact that it can actually withstand up to a 2-to-1 pressure ratio. And what that means is, say for example, you have 60 psi on your cold and you have down to 30 psi on your hot. Now, why would you have that? You know, and we get this actually quite a bit from out east, where they have a tankless coil inside of a cast iron boiler, which is very common out there, and those tankless coils get scaled up. And so as that tankless coil scales up, you're going to get more and more pressure drop, and say now all of a sudden it's down where it's 60 on the cold side, but it's only 25 on the hot side. And the thermostatic element and the shuttle cartridge assembly that's inside of that mixing valve just can't overcome those pressure drops, or the pressure differences, excuse me. But if you have the proper inlet pressures to both sides and you fall within that 2-to-1 range, you're going to be more than okay. Now, on another example, we had a customer recently with booster pumps, and they were having issues with some of our larger mixing valves. And as Kevin had mentioned before, you know, the larger mixing valves do have a minimum flow requirement that does have to be adhered to. But one thing that they were having issues with is they had such a differential cut in and cut out on their boosters that it was just causing the mixing valves to go crazy because they couldn't keep up with how the pressure was differing all the time. You know, if it's a constant differential between the hot and cold, it's not a big deal, but as it bounces all around, it can really cause some issues. So they ended up tightening up the cut in, cut out on the boosters, and everything worked just fine. So great question, Bob.
Yeah, thanks. That was a great explanation, by the way.
Yeah, so one thing that we really wanted to dive in on, and we've talked about this a lot, and I feel like I'm beating a dead horse almost sometimes when I talk about it, because it comes up pretty frequently, is recirculation with not only a high-low, but any mixing valve. So what we've got here on the screen here is a pretty standard diagram showing a tank, a mixing valve, and a recirc. And one thing that's to point out here too is a great reference for a lot of this stuff is going to be hydronics number 11, and Siggy goes through a lot of that stuff really, really well. Another one again is going to be the upcoming hydronics, the recirculation hydronics coming in July. And last but not least, my most favorite reference for this is the webinar we did a number of years ago with Julius Belanco, and he went over a lot of the finer points of domestic hot water recirculation and a problem known as creep. And so when you're looking at this diagram, we've got a single small mixing valve in there. It's a 1017 mixing valve, which is going to be a point of distribution mixing valve, okay, where you're going to put it at the fixture. Now, if you're putting in one of our high-low assemblies, it will act no different as far as how you're piping and balancing your recirculation system. And so you want to follow the exact same rules, and everybody thinks, okay, you bring your recirculation line back and you just plug it into the cold inlet of the mixing valve. But the problem is that recirculation pump is pulling through the mixed outlet of the mixing valve, which means it's pulling not only from the cold inlet but the hot inlet. And the thing that you're going to run into with 1017 style mixing valves is that they really don't have the ability to completely close off one port or the other. And what I mean by that is say for example, if your mixed outlet starts creeping above whatever your set point is, it can't completely shut off that hot inlet. And where that becomes a big problem is buildings with constant recirculation. And more so buildings with constant recirculation where they have down periods where there isn't a lot of demand or little to no demand. Julius talks about this in applications like nursing homes where everybody's in asleep at that point in the middle of the night. And what happens then is, say for example on this drawing here, you see after the recirculation pump or the circulator, you're going to have actually where it branches off into two directions. And one of them goes to the cold inlet of the mixing valve. And you'll notice just upstream of that connection on the cold inlet of the mixing valve is a check valve. And where it branches off and it goes to the other side of that check valve with the other connection from the recirc. Now, if you didn't have any of those valves in there or that check valve in there, what's going to happen is all the flow from the recirc is going to come back and it's going to hit that cold water inlet. And at that point, it's either going to go into the cold water inlet of the mixing valve or it's going to go back through the tank and get heated back up to whatever your tank temperature is and come back to the hot inlet. Now, if you have little to no demand on a constant recirc system, over time, say you lose 5 degrees on your recirc of temperature drop, over time, the mixing valve is going to constantly add a little bit more and a little bit more and a little bit more heat. So then at some point, the hot water line and the recirc line is going to meet the whatever temperature the tank is at. So that could be 140, 160 on up, and that could be a very dangerous situation, as Julius has pointed out in previous webinars. So what we've got here is going to be what I refer to as a return and a bypass line. Okay, so the return goes directly to the cold inlet of the mixing valve, and then there's that check valve just down or upstream of the cold inlet that basically forces all of that to go in one direction, straight into the cold inlet of the mixing valve. From there, you've got that bypass line that goes on the other side of the check that pushes a little bit of flow through the tank. And what you've got here is I think it's important to note that the two valves on there I refer to them as balancing valves because they are balancing valves. And I would recommend using valves there similar to a globe style that has a little bit more flow control as opposed to gate valves or ball valves, especially because those are just more open close valves. They're not a control valve. So what you've got there is the two valves, and the return valve that's going directly to the cold inlet of the mixing valve is typically going to be wide open. And from there, the bypass line with the that globe valve on that one is typically going to be just cracked open enough to where you're going to allow enough flow through the tank to make up whatever temperature loss you're going to have through your recirc. So you want that, you're going to start off with it pretty much closed, and say you've got 115 degrees going through your recirc and everything like that. You're going to start cracking that open until it reaches your 120 if that's what you're shooting for. So that way it's overcoming that temperature loss inside the recirc. So again, whether it's a single mixing valve or a high-low assembly, doesn't matter which, you want to make sure that you're piped and balanced properly. Again, the Julius Belanco webinar is a great resource. And then, just make sure you're doing that because we do get a lot of calls about that. So the next, I don't know if anybody has any questions. That was kind of a lot to digest. Again, we wanted to beat that horse a few more times on the recirculation because I think it's very, very important. But on our next one here, and one thing to mention too, I almost forgot, is on when you're looking at recirculation, Kevin and I have talked about minimum flow requirements for the valves. And in many cases, especially on the smaller mixing valves, your recirculation flow will actually meet and or exceed the minimum flow requirements in your domestic hot water system for the mixing valve. And so what that means is if your recirculation is the flow rate through the mixing valve is meeting or exceeding that minimum flow requirement, then that means your actual system is not going to have any flow requirements at all. So you could be drawing, very little, flow without any issues with instability or, too hot, too cold hunting. So good point there. We've got a great photo here, and I believe it was an excellence entry from a few years ago. And when I saw it, I wanted to buy the gentleman a nice adult beverage, whoever did this, a lady or gentleman, whoever did this. I wanted to buy them a very nice adult beverage because how they did it here was exactly how we talk about piping it with the recirc and the bypass line, or the return and the bypass line, to make sure that you're properly balanced. But one thing that's incredibly unique about this, and Kevin, if you can kind of circle those, is you'll see actually 2 mixing valves there. And those are actually 2 of our small mixing valves, our 521 series mixing valves, and they're piped in parallel. And I think one thing to point out here is that we get a lot of customers that need just a little bit more flow than what our small mixing valve can provide on its own, but they're not quite ready to make that big jump up to a high flow mixing valve or a high low. And so by running them in parallel, you can increase your flow without breaking the bank and without having issues with minimum flow requirements on some of our larger mixing valves. But one thing to really point out here is that the mixing valves coming from the tank, the cold inlets and the hot inlets, you'll notice how they're piped, as they're piped in kind of an equal distant or reverse return kind of fashion here, kind of first in, last out. And that's really important to make sure that you're getting equal flow through each of the mixing valves. But below the mixing valves, you'll notice that we actually have 2 different check valves, and Kevin can kind of circle those. There's the one there around just on the outlet of the recirc to make sure you're not getting reverse flow through the recirc. But then we've got another one on the cold inlet to the water heater, and that's exactly where I had positioned it before, where just above that you've got the return from the recirc going into the cold water inlet and the balancing valve right there. And then just below it, you've got the bypass line that comes in underneath that check valve and goes through the tank. And then that valve there is going to be just basically allowing just a little bit of flow through there to make sure that you're overcoming the temperature loss through your recirculation line. And again, usually those are, especially in residential applications, those are going to be just cracked open. I mean, you're not overcoming a lot, especially if your hot water lines are insulated well and you don't have a lot of issues there. So again, going over a very unique application here with the parallel mixing valves, I think is really cool, and just going over the piping there in kind of a real world scenario as opposed to something drawn with crayons. So next up, we want to bring up another poll question for you guys, and we always appreciate your input. I can't count how many times we get phone calls from contractors, engineers, homeowners too. We get calls from across the board here at Caleffi, and we try to take all that information and put it to good use, because as a company we try to be as innovative and helpful as possible. We always try to make products that are going to help you with your installation, not make your life more difficult. So if you ever have a question about any of our products, or a question about a potential product, don't hesitate to give us a ring, because if we get enough interest in something like that, it's something we can look into. A lot of our products have been because of people calling in, and asking about, can you do this, can you do that? So we want to ask you here with high-low mixing valves, and this could apply to regular mixing valves as well. What is your biggest challenge? Is it going to be sizing it, based on fixture units, or is it commissioning, as far as setting up that high-low, and maybe a callback or something because you're having some issues? Is it recirc issues or maintenance, or something else? And you can always tell us in the responses after the webinar. But Woody, if you can run that poll real quick, we just want to know what you guys are thinking. And I know we have a broad range of people in this webinar, from engineers to contractors to homeowners. Our reps are out there too. I know I've recognized quite a few names in the list here today. So we want to make sure that we are listening to you guys, and I hope you guys know that we're always available for questions after this as well. So I don't know how much longer we're looking at here, Woody, but yeah, I mean, it's great to get feedback. So kind of what we expected. Recirculation issues in the lead by a hair, and then the next one down is sizing. So it's information like this that helps us determine what we provide for you for technical literature. And as many of you know, we try to lead the pack the best we can with constant technical information and good information, not just sales information. And we try to provide that unbiased information for you guys to make good decisions and do a good job, make your life easier. So to kind of sum things up here today, we wanted to go over a few kind of big bullet points. The first of which is that low flow or flow below the minimum requirements of the mixing valve is going to result in unstable mixed outlet temperatures, and it could require, or could run into hunting, too hot, too cold, uncomfortable showers, things of that nature. And that the larger mixing valves do require, or do give you more flow, but you got to be really careful of those minimums, because we've got some of the larger ones that have minimum flow requirements of 4.5 or almost 9 gallons per minute, and they work well when they're applied properly, but it's those calls that we get where they're not working quite well, they're hunting and things of that nature that we want to try and ward off. So the high-low mixing valve that we're offering now is a solution to that problem, where you need the high flows, but you can't meet the minimums all the time. So we're always open to more ideas on that stuff, but we wanted to bring the solution to market because I've talked to a lot of people on the phone, and I've had to refer them to other manufacturers because we don't have something to offer them, and so this was our response to that. Again, it was your input that really helped with that. The next big bullet point is the 20 PSI differential. We talked about that. I mean, it's kind of a good idea just to make sure you've got enough pressure at your fixtures, but you want to make sure you're not running into velocity issues, erosion, corrosion, and probably the first thing you're going to notice is noise. I've had a few valves in the lab screaming over the years, and nobody wants that in their basement at all. So, and the next thing, when you're doing recirculation, balancing valves are very crucial, not only on the risers or whatever direction you're going or coming from with the recirc, but on the return and bypass lines as well that are feeding water to either the cold inlet of the mixing valve or the tank. They're a very good idea for the return lines back, but the lines going to either place are absolutely important. Again, as I had mentioned before, the minimum flow rate of the mixing valve just might be met by the recirculation. And so it's something you can kind of fudge a little bit, but the thing there is that you need to know that's if you're using the recirculation. So if your recirculation is on a timer or it's temperature based or anything of that nature, you got to be really careful with that, because if you're doing constant recirc and you're meeting that minimum flow, you're good to go. But if it's shutting on and off, it's something that you got to be careful of. And then last, we're going to open things up to some of the questions. I'm sure there's a few of them, Mark or Bob, but let us know what you're thinking. We want to hear from you.
One thing I'd like to add too, Cody, is sometimes I know you get the call and the symptom is that our valves are hunting all over, the temperature is inconsistent or thready, it's warm, it's hot, it's cold. These valves, when you put them in systems that have hard water, they do scale up from time to time, and you may need to take them apart and delime them, or soak them in some vinegar, or run a delimer through it, because it can be a same symptom presentation where you think the valve is bad or it's a recirc issue, and it could be the valve is just sticking up in there from minerals in the water. And by the way, the hotter that you run that domestic water heater temperature going into that valve, the higher percentage of minerals that precipitate out. So if you're going to crank a tank up to 150, 160 degrees to boost the output of that tank, then mix it down through a mixing valve to 110 or 120, just know that you're going to get a lot of minerals precipitating out, and that valve is going to need to be serviced. Now, the good news is on our high-low mixing station, you can see that we had some valves that you can isolate those mixers. So if you do have to take them apart and soak them in vinegar, or rebuild them or clean them out or something like that, it makes it a little bit easier to do that. So as far as questions, I think I threw a couple in there. Mark, do you have any that you were monitoring there? I watched a couple of them as we were going here.
Well, as they're coming in, it seems like some of these are already getting addressed, so I'll try to talk about some that I haven't. Let's talk about the water coming in. Do you have to be concerned with mixing valves as it relates to water treatment chemicals, chlorine, for example?
That's a great question. All of the seals and everything inside of our mixing valves, as well as our the diaphragm and our PRVs, they're going to be a peroxide cured EPDM, which is going to be a highly resistant form of EPDM to chloride. So basically, no, I wouldn't be too worried unless you're really off the charts with really high chlorides. So.
Okay, good question or good answer. In recirc pump sizing, the question is, do I just consider the resistance in the small thermostatic mixing valve loop and not the larger for my pump sizing?
That's a great question. When you look at your recirc pump sizing, I would say look at the loss through the small mixing valve by itself. I mean, like on our, especially like on our high-low. Our high-low is going to be, for a range of 1 to 50 gallons per minute, and chances are you're not going to have a recirc line that's pushing 30 gallons per minute. So most of the time that flow rate should just be going through the small mixing valve, because you're not going to have enough differential to actually open up the PRV. So for that, I would look at the pump curve, or the characteristics chart for the small mixing valve. So
okay. Another question came in concerning balancing valves used in hot water recirculation loops. The question is whether I use a high-low mixing valve or another type of mixing valve. Does that have any effect on what kind of balancing valve I should use?
Well, that's kind of a good one, because I mean, there's fixed balancing valves. There's going to be pressure independent balancing valves, and then we've actually introduced a recent balancing valve that is based on temperature, which is very unique. And I don't think it's going to be so much a factor of what type of balancing valve you should use, as how the pump is sized or applied, whether it be like a constant speed or a constant pressure. I don't know if you have anything to add on that, Kevin or Bob. I mean, I think I kind of nailed that one down, but.
No, I think you're right. It depends on the application. There's a good application if you've got multiple branches off a recirc that are thermal mixing valves, our new valves would be an excellent valve for that, because they're self-balancing on temperature. So you wouldn't have to go around to all those different loops and try and manually balance them out. But if you're just doing a single loop, the balancing valve that Cody showed earlier is a good one, because you can make really fine adjustments on it and dial in that flow, so you get that, you avoid that temperature creep issue. So it really depends on the application on which valve you would select, but certainly look at our thermoset or the 116 valve for big complicated piping, recirc piping projects.
And our 132 pluses, the Quicksetter pluses, the lead-free models that we've had out for a while now have really started to take off, and we're offering them in sweat, press, PEX. I mean, they're all across the board, and those are so easy to set, and so no requirements there as far as a balancing contractor, and you can just you can get the job done on your own. So.
Yeah, some of the other questions, I knew Drew just sent a good one in, and a lot of these are going to be answered in Siggy's when he does his in July, as far as that sizing the recirculation pipe and the pump and the heat loss through that. So I don't want to ignore questions here, but I think you'll get a really good answer. And somebody wanted like a written explanation of how this balancing works with the recirc on a thermostatic valve. I know Siggy's going to get into that pretty deep, because this is, I got to say, like Kevin and Cody, got to just say this is the most frequent question. I think our video's been viewed like 80,000 times on the one that Julius Blanco did on this. So we know that it's a big problem out there, a big concern, and not a lot of people understand exactly how that works and how it sets up. I mean, Cody explained it really well in this presentation, but sometimes to have a drawing in front of you as you're going through it helps also. So go back to our issue number 11. We talked about it, but we're gonna get in that a little bit deeper in July when Siggy comes back with the new hydronics issue.
Hey Bob, our March Coffee with Caleffi webinar was on balancing domestic hot water, so there's some really good detail in there on that.
Yeah, we've covered it a few different times on that one, like Kevin just noted, and the one that Julius did for us, and the one Siggy's going to be doing, and we touched on it here again in this presentation. So, yeah, we'll help you. Just let us know what you need out there, or send us, a little schematic that you draw up or anything, and we can talk you through it maybe.
And then Mark, Bob, I don't know if we have anything else that we want to get to, or.
I think this is a fair question. How about digital mixing valves versus high-low combination valves as we showed?
Well, digital mixing valves are becoming more and more popular, especially if you need to tie into the building automation system, of course. Also, if you're going to do any kind of disinfection of a recirculation line, you can't really do that effectively with a high-low thermostatic mixing valve. That's when you need to go to a digital mixing valve. So yeah, and there are a few other advantages. Of course, they're more expensive, but they you can do more with them. You can do overrides, you can do data logging, data gathering, and just provide a little more information compared to a standalone thermostatic high-low.
And where will we play in that market, Kevin? Can you give us a little insight?
Well, we're working on a digital mixing valve. In fact, we'll be coming out with that later this year. So, sneak preview, folks. Watch for that.
And we'll certainly have a good webinar on that. I think EMV is another term I see out there: electronic mixing valves, digital mixing valves, as opposed to TMVs, which are thermostatic valves. So that's some of the lingo that you're starting to see out there, and we'll certainly have a great product for that. Once we have it ready to go, we'll tell the world about it.
Okay, well, I want to thank everybody for attending. We really appreciate your time. Send those questions in. I will look over every one of them and give you a reply. And until next time, anything else, Bob?
No, good
All
job.
right.
Thanks.
Thanks, everybody. Bye.
Bye-bye.